Alright, in this video we're going to be looking at an optimization example. In this example I'm going to read it. It says find the dimensions of an open box that has a volume of 10 cubic feet and that uses the least amount of material in its construction. Assume the box has a square base. So the first important thing when you're doing an optimization problem, the first important thing would be to determine what we want to optimize. And in this case we want to find the least amount of material in its construction, using the least amount of material. So in that case the material would be, in this case we would be looking at, since it's in feet here, we'd be looking at how many square feet. So what kind of piece of cardboard or whatever we would need to cut this out of, how much, so that we can minimize it. If it's a cardboard box, we'd want to minimize the cardboard that we would use, the least amount of material. So in this case the material we're using is in how much cardboard, so we're looking at an area. So our first question here, our first important question here would be to answer that, what are we optimizing? And we're optimizing an area. So we would want to write down an area formula so that we can try to optimize that formula, make it the best solution that we possibly can. So we would then go back and look at what we're given. All right, it says find the dimensions. Okay, we're not given any dimensions. We have a volume, so there is a volume of 10 cubic feet. So volume equals 10. In this case, we know 10 feet cubed. So we know that, that's given. This is what we're looking for. We already wrote that down, and we also are saying that the box has a square base. So that means that some of the dimensions are the same because it's a square, so some of the dimensions are going to be the same. So I'm going to go down here and I'm going to label some of the dimensions because we're going to have to write a formula. The second important thing here is to write a formula or a relationship for this optimization, but we need to have some variables or unknown quantities written down in this problem. So first I would look at what it says here. It has a square base, so that means the sides on the bottom are going to be the same. I don't know what they are, but they're the same, so I can write x for both of those sides. Okay, and then the height is going to be a different letter or a different value. We don't know that it's a square going on the sides, so we would use a different variable here. So in this case we're going to have two variables. Usually there are three, but in this case, since we have a square base, two of the variables are the same. So we're going to have, the bottom is going to be x by x, and then the side is going to have a y distance here. Alright, so now that we've labeled it with some variables, we want to write this optimization requirement. So we're going to have to find an area. So what we want to do is find the area of this box, and we want to write this out in terms of the area. In this case we have four sides and a bottom. Because it's an open box, we don't have a top. Alright, so let's start with the bottom, because it's just, the bottom is x times x, or x squared. So that's the bottom of the box, so that's the area of the bottom. And then we're going to have this side is going to be x times y, or xy. This side is x, this is also y here, so this, all of these sides are y going up, y, and over here it's y as well. So this side is also x times y, so it's got an area of xy. The back is x here, y there, so it's also got an area of xy. And this side over here also has an area of xy. So each of the sides have the same area, so there's 4 of those, 4 sides that have an area of xy. So this would be our relationship that we would look at for optimizing. We want to figure out the least amount from this problem. Now we have too many variables to look at here to optimize this. So what we're going to need to do here is we're going to have to take a look at our other piece of given information in red, that the volume is 10 cubic feet. So what we would look at there is, if the volume is 10 cubic feet, how do we find the volume of this box? Well, the volume of the box is x times x times y, length times width times height. In this case, x times y. So what we're really going to have here is we're going to have a volume of 10 that equals x squared. X times x is x squared times y. So we're going to have this relationship for volume. Well, what we're going to need to do here is I'd like to have this problem in terms of one variable. So what I'm going to do here is I'm going to take my volume formula here and I'm going to solve it for y. So I get y equals, we're going to divide both sides by x squared. Alright, x squared. Okay, so we're going to get 10 over x squared as our y value. And then I'm going to substitute this. I'm going to take this equation and I'm going to substitute it right here for this y. So I'm going to take this 10 over x squared and I'm going to put it right there, so that I have one variable, because I'm going to need to look at it as a function of one variable. I want to write it as a function of the length of the base. Right now it's a function of the length of the base and the height. But I want to be able to write it as a function of the length of the base. So in doing so, I'm going to rewrite this area formula as x squared, x squared plus 4x times 10 over x squared. And I want to simplify this a little bit so that I can not have as many. This will simplify here so we can write it as a little bit simpler problem. So it's going to be x squared. I can't simplify that part because we're not adding anything to that. Now here we're going to multiply 4 times 10, so we're going to get 40 in the numerator. Now this x will reduce with one of these in the numerator or denominator, so we're going to end up with 40 over x. Okay, so this is what I'm looking at as my function of area. Now in an optimization problem, I'm looking for the highest or lowest value, so I'm going to use my graphing calculator here to find that lowest value. So I'm going to take my calculator, now that I have it as a function of one variable, I'm going to take my calculator and look at the graph of this and see if I can find its least value. So in doing so, we want to make sure we go here and we're going to take this and we're going to write x to the second plus 40 divided by x. We're going to take a look at that graph and see if we can find a minimum value. Now we would probably want to look at what values could we put in first. Since the area is or the volume is 10, I don't think that my dimensions are going to be any bigger than 10. So my window here, I would probably go just a little bit into the negative range, even though, just so that we have a little room on the graph. But I'm going to go up to 10 as our maximum, and I'm not sure what my area is going to be. So I know it's not going to be negative, so we're just going to leave a little negative so that it runs into that. So I'm going to go up to 20 here. I'm not sure what my area is going to be. Area is my y value. We're going to go by 2 here. We'll push graph here and see if I can see this graph and find its minimum area. It doesn't look like I can see it. It looks kind of like this went shooting up here. If I do trace, 4.5 is 29. So when I put in 20, it's not high enough. The first value that I pushed on trace is 29. So I need to go back and set my window at more than 20. So 29 was at 4.5. So I'm going to go up to 50 just to see if I can do that. See if I can see it. I'm using that trace, that one trace button to help me make another guess about my maximum. Now let's push graph there and see if I see anything. So there I do now see the graph, and I see where it comes down to be a minimum. So this is going to be where my least amount of material is going to be. Okay, so I'm going to need to look and find that value. So using a calculator, you would use calculate, we would find the minimum. That's the 3. It's going to ask for a left bound, so we would move to the left of the minimum. Hit enter. We would move to the right of the minimum. Hit enter. And guess I moved close to where I think it might be, and I push enter again. And it's going to tell me my minimum value. So this is telling me that my minimum value happens at when my base is about 2.7. So my x value here is approximately 2.7, and my area is going to be 22. So in this case, my x value, in this case, x is going to be approximately 2.7 feet for that dimension. And my area, which is my y value here, is going to be about 22.1 square feet. That's what we're finding area here on y. Now if I really wanted to know all the dimensions, it says find all the dimensions, so I would then need to go back and put my 2.7 back into this equation to find out what y is. Put it back in this equation so I can get my dimensions this way. So if I do that, I stick it back into that equation, I'd have 10 over 2.7 squared is equal to y. Alright, so I'd go over here to my calculator, and I'd go back to quit, and I'd use 10 divided by 2.7 squared, and I would get approximately 1.4 for y. So my answers for my dimensions are going to be approximately 2.7 feet and 1.4 feet. So those would be my dimensions of the box. It's going to have a square base of 2.7 by 2.7 and a side of 1.4, and it's going to give an area of 22.2 feet.